Concept of equilibrium and the equilibrium constant. Few chemical reactions proceed in only one direction. Most are reversible, at least to some extent. At the start of the reversible process, the reaction proceeds toward the formation of products. As soon as some product molecules are formed, the reverse process begins to take place and the reactant molecules are formed from product molecules. Chemical equilibrium is achieved when the rates of the forward and reverse reactions are equal and the concentrations of the reactants and products remain constant. Chemists are particularly interested in chemical equilibrium processes, such as the reversible reaction involving nitrogen dioxide and the nitrogen tetroxide. The process of the reaction can be monitored easily because dinitrogen tetroxide is colorless gas, whereas nitrogen dioxide has a dark brown color that makes it sometimes visible in polluted air. Suppose that dinitrogen tetroxide is injected into an evacuated flask. Some brown color appears immediately, indicating the formation of nitrogen dioxide molecules. The color intensifies as the dissociation of dinitrogen tetroxide continues until eventually equilibrium is reached. Beyond that point, no further change in color is evident because the concentrations of both dinitrogen tetroxide and nitrogen dioxide remain constant. We can also bring about an equilibrium state by starting with pure nitrogen dioxide. As some of the nitrogen dioxide molecules combine to form dinitrogen tetroxide, the color fades. Yet another way to create an equilibrium state is to start with a mixture of nitrogen dioxide and dinitrogen tetroxide and monitor the system until the color stops changing. These studies demonstrate that the preceding reaction is indeed reversible because a pure component reacts to give the other gas. The important thing to keep in mind is that in equilibrium, the concentrations of the nitrogen tetroxide to the nitrogen dioxide and of nitrogen dioxide to the nitrogen tetroxide are still going on. We don't see a color change because the two rates are equal, and the removal of nitrogen dioxide molecules takes place as fast as the production of nitrogen dioxide molecules and the nitrogen tetroxide molecules are formed as quickly as they dissociate. The gas concentrations are expressed in molarity, which can be calculated from the number of moles of gases present initially and at equilibrium, and the volume of the flask in liters. Note that the equilibrium concentrations of nitrogen dioxide and the nitrogen tetroxide vary depending on the starting concentrations. We can look the relationship between molar concentrations of nitrogen dioxide and the nitrogen tetroxide present at equilibrium by comparing the ratio of their concentrations. The simplest ratio, that is this one. In this formula, K is a constant, and note that the exponent 2, this one, in this expression is the same as the stoichiometric coefficient of nitrogen dioxide in this equation. We can generalize this phenomenon with the following reaction at equilibrium. And for the reaction at particular temperature, K equilibrium constant, we can express like this. Equation was formed by two Norwegian chemists, Gullberg and Waage, in 1864. It is the mathematical expression of their law of mass action, which holds that for a reversible reaction at equilibrium and constant temperature, a certain ratio of reactant and product concentrations has a constant value K, equilibrium constant. Note that although the concentrations may vary, as long as a given reaction at equilibrium and the temperature doesn't change, according to the law of mass action, the value of K remains constant. The equilibrium constant then is defined by a quotient, the numerator of which is obtained by multiplying together the equilibrium concentrations of the products, each raised to the power equal to its stoichiometric coefficient in the balance equations. Applying the same procedure to the equilibrium concentrations of reactants gives the denominator. The magnitude of the equilibrium constant tells us wherever an equilibrium reaction favors the products or reactants. If K is much greater than 1, the equilibrium will lie to the right and favors the products. Conversely, if the equilibrium constant is much smaller than 1, the equilibrium will lie in the left and favors the reactants. There is a general rule that helps us to predict the direction in which an equilibrium reaction will move when a change in concentration, pressure, volume, or temperature occurs. The rule, known as the Digitalis principle, states that if an external stress is applied to a system, at equilibrium, the system adjusts in such a way that the stress is particularly offset as the system reaches a new equilibrium position. The word stress here means change in concentration, pressure, volume, or temperature that removes the system from the equilibrium state. We will use the Digitalis principle to assess the effects of such changes. Changes in concentration. Iron 3 thiocyanate dissolves readily in water to give a red solution. The red color is due to the presence of hydrated ion, this one. The equilibrium between undissociated red color ion and iron 3 plus and thiocyanate ions is given by this equation. That happens. What happens if we add some sodium thiocyanate in the solution? In this case, the stress applied to the equilibrium system is an increase the concentration of thiocyanate from the dissociation of sodium thiocyanate. To offset this stress, some iron 3 ions react with the added thiocyanate ions, and the equilibrium shifts from right to left. Consequently, the red color of sodium of solution deepens. Similarly, if we added iron 3 nitrate, for example, or our iron 3 salt to the original solution, the color, red color, would also deepen because the additional iron 3 ions would shift the equilibrium from right to left. Now suppose we add some oxalic acid to the original solution. Oxalic acid ionizes in water to form oxalate ion, which binds strongly to the iron 3 plus ions and form some strong complex, stronger coordination compound. Because of this, this complex oxalate ion removes free iron 3 plus ions in solution from the solution. Consequently, more iron thiocyanate units dissociate and the equilibrium shifts from left to right. The red solution will turn yellow due to the formation of complex of iron 3 plus and oxalate ion, and because of remove of 3 iron plus ions. This experiment demonstrates that all reactions and products are present in the reacting system at equilibrium, and tell us that increasing the concentrations of the products shifts the equilibrium to the left, and decreasing the concentrations of products shift the equilibrium to the right. These results are just as predicted by Le Chatelier's principle. Changes in volume and pressure. Changes in pressure originally don't affect the concentrations of the reacting species in the condensed phases, like solid phase or liquid phase, because liquids and solids are virtually incompressible. On the other hand, concentrations of the gases are greatly affected by changes in pressure. You can see at this equation to see how pressure can affect the molar concentration, because N is the amount of substance divided by volume of substance, the molar concentration. So pressure can affect the molar concentration of gases. So pressure and volume are related to each other inversely. The greater the pressure, the smaller the volume, and vice versa. Suppose that the equilibrium system, already known equilibrium system, is in a cylinder fitted with a movable piston. But what happens if we increase the pressure on the gases by pushing down on the piston at a constant temperature? Because the volume decreases, the concentration of both nitrogen dioxide and the nitrogen tetroxide increases. Note that the concentration of nitrogen dioxide is squared in the equilibrium constant, this one. So the increase in pressure increases the numerator more than the denominator. In general, an increase in pressure favors the net reaction that decreases the total number of moles of gases. The reverse reaction in this case. And a decrease in pressure or increase in volume favors the net reaction that increases the total number of moles of gases. Here, the forward reaction. For reactions in which there is no change in the number of moles of gases, a pressure or volume change has no effect on the position of equilibrium. Changes in temperature. A change in concentration, pressure, or volume may alter the equilibrium position, that is, the relative amounts of reactants and products, but it doesn't change the value of the equilibrium constant. Only a change in temperature can alter the equilibrium constant. To see why, let's see our reaction. The forward reaction is endothermic. So the reverse reaction is exothermic. Endothermic reaction is that reaction that absorbs heat. Exothermic reactions is reactions that releases heat. At equilibrium, at a certain temperature, the heat effect is zero because there is no net reaction. If we treat heat as if it were a chemical reagent, then a rise in temperature adds heat to the system, and a drop in temperature removes heat from the system. As with a change in any other parameter, the system shifts to reduce the effect of the change. Therefore, temperature increase favors the endothermic direction of the reaction. From left to right of the equilibrium equation, which decreases dinitrogen tetroxide concentration and increases nitrogen dioxide concentration. A temperature decrease favors the exothermic direction of the reaction. From right to left of the equilibrium equation, which decreases nitrogen dioxide concentration and increases dinitrogen tetroxide concentration. In summary, a temperature increase favors an endothermic reaction, and temperature decrease favors an exothermic reaction. The effect of a catalyst. We know that a catalyst enhances the rate of the reaction by lowering the reaction's activation energy. However, a catalyst lowers the activation energy of the forward reaction and the reverse reaction to the same extent. We can therefore conclude that the presence of a catalyst doesn't alter the equilibrium constant, nor does it shift the position of an equilibrium system. Adding a catalyst to a reaction mixture that is not an equilibrium will simply cause the mixture to reach equilibrium sooner. The same equilibrium mixture could be obtained without the catalyst, but we might have to wait much longer for it to happen. Electrolytic properties. All solutes that dissolve in water fit into one or two categories: electrolytes and non-electrolytes. An electrolyte is a substance that, then dissolved in water, results in a solution that can conduct electricity. A non-electrolyte doesn't conduct electricity, then dissolved in water. This picture presentation shows an easy and straightforward method of distinguishing between electrolytes and non-electrolytes. A pair of inert electrodes is immersed in a beaker of water. To light the bulb, electric current must flow from the one electrode to another. Thus completing the circuit. Pure water is a very poor conductor of electricity. However, if we add a small amount of salt, for example, sodium chloride, a bulb will glow as soon as the salt dissolves in the water. Solid sodium chloride is ionic compound, breaks up into sodium plus and chlorine minus ions, then it dissolves in water. The sodium plus ions are attracted to the negative electrode and the chlorine minus ions to the positive electrode. This movement sets up an electric current that is equivalent to the flow of electrons along a metal wire. Because the sodium chloride solution conducts electricity, we say that sodium chloride is electrolyte. Pure water contains very few electrons, so it cannot conduct electricity. Comparing the light bulb's brightness for the same molar amounts of dissolved substances helps us to distinguish between strong and weak electrolytes. A characteristic of strong electrolytes is that the solute is assumed to be 100% dissipated into ions in solution. By dissociation, we mean the breaking up of the compound into cation and anion. Thus, we can represent sodium chloride dissolving in water by using this reaction. This equation says that all sodium chloride that enters the solution ends up as sodium plus and chlorine minus ions. There are no undissociated sodium chloride units in solution. Water is a very effective solvent for ionic compounds. Although water is an electrically neutral molecule, it has a positive region, hydrogen atoms, and negative region, oxygen atom, or positive and negative, or we can call it positive and negative poles. For this reason, it is a polar solvent. Then ionic compounds such as sodium chloride dissolves in water. The three-dimensional network of ions in solids is destroyed, and the sodium plus and chlorine minus ions are separated from each other and undergo hydration, the process in which ion is surrounded by water molecules arranged in a specific manner. Each sodium cation is surrounded by a number of water molecules oriented in their negative poles toward the cation. Similarly, each chlorine ion is surrounded by water molecules with their positive poles oriented toward the anion. Hydration helps to stabilize ions in solution and prevents cations from combining with anions. Acids and bases are also electrolytes. Some acids, including hydrochloric acid and nitric acid, are strong electrolytes. These acids are assumed to ionize completely in water. For example, then hydrogen chloride gas dissolved in water, it forms hydrated hydrogen plus and chlorine minus ions. This one. In our words, all the dissolved hydrogen chloride molecules separate into hydrated hydrogen plus and chlorine minus ions. Thus, then we write HCl aqueous solution. It is understood that it is a solution of only hydrogen plus and chlorine minus ions, and that there are no hydrated hydrogen chloride molecules present. On the other hand, certain acids, such as acetic acid, for example, which gives vinegar its tart flavor, don't ionize completely and are weak electrolytes. We represent the ionization of acetic acids such as this, where acetate is acetation. We have acetation and also hydrogen plus ion, and the ionization of acetic acid is written with a double arrow to show that it is a reversible reaction. That is, the reaction can occur in both directions. Initially, a number of acetic acid molecules breaks up into acetate ion and hydrogen plus ions. As the time goes on, some of the acetate and H plus ions recombine into acetic acid molecules. Eventually, a state is reached in which the acid molecules ionize as fast as the ions recombine. Such a chemical state, in which no net change can be observed, is called chemical equilibrium. I already told you about it. Acetic acid then is a weak electrolyte because its ionization in water is incomplete. By contrast, in a hydrochloric acid solution, the H plus and chlorine minus ions have no tendency to recombine and form molecule hydrogen chloride. We use a single arrow to represent complete ionization. Single arrow.